Hello! In this video, I'd like to talk about regular functions. As we saw all the way back in my video on regular relations, it's possible to reason about functions using finite state automata. In that video, for instance, I talked about how we can represent addition using a finite state automaton. To begin with, we need to turn addition from an operation on numbers to an operation on words, on strings. And we can view numbers as strings in base 10, for instance. Our next step was to relationalize this function, and this has been something that's been incredibly helpful throughout this video series. Instead of talking about a function that takes in two strings as inputs and outputs a string representing their sum, we can instead talk about a relation that takes in three strings as inputs and tells us if the third is the sum of the first two. And then finally, we still need to be able to have a finite state automaton that accepts multiple inputs. We need a finite state automaton that takes in a triple of strings and tells us whether or not the sum of the first two is equal to the third. And it turns out that the right way to do that is to read our inputs in parallel, to read all of the first characters, and then all of the second characters, and then all of the third characters, and so on and so forth. And of course, if the inputs aren't the same length, we're going to have to pad the shorter ones out with some sort of padding character to make them all the same length. As we've seen throughout this video series, this notion of a finite state automaton that can accept multiple inputs corresponds to first-order logical formulas that can take in multiple inputs. And so ultimately, our notion of regular function is going to correspond exactly to the functions that are describable in the first-order logic of the word logic. Hence my interest in them. We're only a translation away from the set of functions that we can talk about in weak S1s. So just to get this formally, a function on words is regular if there's some deterministic finite state automaton, or if this collection winds up being regular, of inputs of the form x1 through xn comma y with y equal to f of x1 through xn. And then these words, they might not be equal length, so we're going to have to pad them all to length, and then we're going to want to read in all of these inputs in parallel. All of the first characters, and then all of the second characters, and then all of the third characters. So for instance, if we have a function where f of ABBA, b is equal to AA, in order to express that, our deterministic finite state automaton is going to have to accept when we feed in these three words in as input. And in order to do that, we're first going to have to pad them all to length. So the longest input is length 4, so we're going to have to pad them all to be length 4. I like to use octothorpe characters for this, but you can use any character that's not already in your alphabet. And then we read these inputs in parallel. So the first character that we're going to feed to our finite state automaton is actually this vector here, ABA. And you can check that when we do this construction, there's only going to be finitely many such vectors that show up. So really we're working with a finite state automaton on just a larger alphabet. Then the second character that we read in is B octothorpe A, and so on and so forth. And our deterministic finite automaton is going to accept once we've finished reading in these four characters. One of the really basic regular functions is one that applies a function character-wise. Suppose that we have a function that takes in two characters from the alphabet AB and spits out a character from the alphabet CD. We can then apply this function character-wise to two words of equal length. In order to work out the first character of the output, we take the first two characters of the input and we run them through the function f to get C. Then we take the second two characters of the input and we run them through the function f to also get C. And then finally we take the third two characters of the input and run them through our function to get D. And it's super easy to build a finite state automaton that checks this. It just has to look at inputs like this and check every time it reads a character, right? The first character we're going to feed in is ABC. It needs to check, is it the case that this here is f of AB? And sure enough, it is. So our automaton doesn't really need to keep track of any data at all as it reads through a word. It just has to see, are all of the triples that we input into the automaton valid triples according to this function here? If so, it accepts, and if not, it rejects. So really we need two states. One state that says everything is fine, and that's an accept state, and then we have a failure state where if we see anything that's not okay, any characters that we don't want, we go into that state and we stay stuck in that state, and that's not an accept state. This here is an extremely important function for being able to fit together two regular functions that operate on slightly different alphabets, and for doing various encoding tricks. The regular functions also include some basic string operations. I'll let you try to figure out what the finite state automata are for the function that removes the last character of a string. I'm going to call this operation trunc for truncation. And it's important to remember that we've removed a character at the end. So you can remember that because there's characters at the end that we've removed. I'm also going to want to talk about the function that removes a first character of a string. I'm going to call that function rest. It ignores the first element of the string and takes the rest of it. And we can also talk about functions that add an a onto the beginning of a word or add an a onto the end. This last operation is our basic successor a operation in the word logic. And I'll just put the a before the s to indicate prefixing an a to the word. We can also define regular functions piecewise. So for instance, f of x is the constant string bb if the number of a's is odd, and otherwise it's the input. So we can do this provided that each of these functions is regular. So a constant function is a regular function, and the identity function is also a regular function, and that the pieces are regular as well. Right? We can define a finite state automaton to determine whether or not the number of a's in a word is odd or even. The idea here is that we just merge together the three automata. The automata that recognizes this function here, the automaton that recognizes this function here, and then another automaton to determine whether or not the number of a's is odd or even. And when we get to the end of the input, we ask is the number of a's odd or even automaton, which is the case, and based on that, then we ask one of these two automata whether or not we should accept or reject. Regular functions can actually do some pretty complicated stuff. We can, for instance, have a function that turns all of the a's in the input that are next to b's into b's. So an input like would turn into, and I'll let you try to figure out how to build a finite state automaton to recognize inputs like this. It's a little bit tricky. If you see an AB, then it could either be the case that we're going to see a B in the input, or we've just seen a B in the input, and you have to handle these two cases separately. Another thing that we can do is take any deterministic finite state automaton and construct a regular function from it that takes in an input and outputs the run that we would get, the sequence of states that we would wind up being in for that particular finite state automaton. For instance, suppose we have a finite state automaton that has an input and a run that looks like this. So it starts off in state 0, and then it reads an A and transitions into state 1, then it reads a B and transitions into state 2, and so on and so forth. If we call this finite state automaton M, I will denote this function by run sub M. One of the things that's really awkward about this function is that the length of the output is one more than the length of the input. And so we can fix that by either removing the first character or removing the last character. It's really natural to want to remove the first character because, after all, this state here is just the start state of our finite state automaton. It doesn't reflect any information about the input. For that function, I'll call it run rest sub m. But actually, after having rewritten my thesis several times in order to try to get this notation to work nicely, I found it better to work with the run map that gets rid of the last character. I'll call this function run trunk sub m. Essentially, we just take the run m function and then we apply trunk to the result in this case, and in this case we're applying rest to the result. This might seem like a strange choice, but actually it's fairly easy to take the output of this function here and advance the automaton one step to get this output here. We just apply the transition function for this automaton character-wise. The transition function, when we're in state 0 and we read an A, takes us to state 1. And we know that was something we expressed up here. But going one step backwards isn't always possible. It's not always possible to recover this information from this information just by applying a character-wise function, because reading in a character might apply a non-reversible transformation to the states. So it's kind of gross, but I like working with this particular input to run map. There's a specific type of automaton that I'd like to look at the input to run maps for, and that's the accumulator automaton for a particular monoid. So here it's a finite state automaton whose input characters are elements of the monoid, whose states are the elements of the monoid, and all of the states are going to be accept states. We're not really interested in accepting or rejecting things. We're interested in looking at the runs of this automaton. Its start state is going to be the identity element of the monoid, and if we're in state A and we read character B, then we'll wind up in state A dotted with B, where this is whatever the monoid operation is. So in general, if we read in the sequence of characters A, B, C, D, we'll start off in the identity element state, and then we multiply by A on the right. So E dot A is just going to be A, because this is the identity element of the monoid. And then we do A dot B to get the next element, and we have to calculate this in the monoid. But I'll just write this because I want to do this in general first. So I'm just going to write this as AB. And then if we're in state AB and we read a C, we're going to wind up in state ABC. And if we're in state ABC and we read a D, we wind up in state ABCD. This automaton here is essentially calculating cumulative sums. Another way of looking at this is that the kth element of the run is just the product in the monoid of the elements before it, the first k elements of the input. Note that this product here is empty if k equals 0, so r sub 0, the first element of the run, is just the empty product, which is the identity element in the monoid. Let's take a look at the specific example where our monoid is addition modulo 10. Let's say we wanted to input the string 5, 6, 7, 8 into the accumulator on this addition modulo 10 operation. The start state would be the identity element for this monoid, that is 0, and then we do 0 plus 5 to get the next state, that'll be 5. Then we do 5 plus 6. Remember, this is modulo 10, so that's 1. Then we do 1 plus 7, that gives us 8. and then we do 8 plus 8, which gives us 6. Our automaton has calculated successively 5, 5 plus 6, 5 plus 6 plus 7, and 5 plus 6 plus 7 plus 8. It's only important that our monoid be finite, so that our corresponding finite state automaton is finite, but this is a really useful function even for infinite monoids. I also want to quickly talk about a non-example of a regular function. There are several different notions of functions that correspond to finite state automata. Regular functions are the ones that I care about because they're most closely related to the corresponding logics that I'm studying. But there are other notions of functions. For instance, there's something called a finite state transducer. And the key feature about these is that as they read in input characters, it's optional whether or not they want to write a character to the output. So for instance, one of these automata can compute the function that removes all of the a's from a word. We can construct a finite state transducer that goes through the input word character by character, and if it sees a C or a B, it writes it to the output, and if it sees an A, it doesn't write anything. So this automaton will write CBC to the output, and then for each of these A's, it's not going to write anything, and then it will write these B's to the output. And so it's very easy to build a finite state transducer that removes all of the A's from a word. But it's worth noting this is not something that we can recognize with a finite state automaton. This is not a regular function. If we pad to length and fed this into a finite state automaton, what it would have to do is it would have to check that this sequence of characters here shows up in duplicate over here. In this example, I've left this sequence of characters short, but it could be arbitrarily long, and the finite state automaton would have to remember that arbitrarily long sequence of characters until after the string of A's to check to make sure that it showed up again character for character at the end of the word. So this automaton would have to have enough memory to store arbitrarily long strings. In other words, more than a bounded amount of memory. So this is a pretty good test if you find yourself dealing with some sort of notion of functions that's related to automata theory somehow, and that notion of function includes the functions that can remove all of the A's from a word, then you're not dealing with regular functions. You're dealing with something stronger. I'd like to introduce some notation for talking about functions on strings. I want to say that a function is causal if the kth character of the output depends only on the kth character of the input and characters before it. And I want to say that a function is strictly causal if the kth character of the output depends only on characters strictly before the kth character of the input. And this is in particular useful for talking about the input to run maps. For any deterministic finite state automaton, the run map and the truncated run map are both strictly causal functions. The first character of the output is the start state of the automaton, and so it's not going to depend on the input at all, just on what automaton we picked, just on the function we're working with. The second character of the output is what we get when we read in the first character of the input in the start state. And so the second character of the output only depends on the first character of the input, and so on and so forth. The key distinction between these two functions here is that the second one is length preserving. The length of the input is equal to the length of the output. And again, we're missing that last state here. On the other hand, the run rest map is just causal. The first character of the output depends on the first character of the input, right? This is what we got into when we started out in the start state and read the first character of the input. Here when I say depends on, I mean that if we change any of the other characters of the input, it's not going to change this particular character of the output. Once we've determined what these characters of the input are, this character of the output is determined. It will also be useful later on to be able to talk about reverse causal and strictly reverse causal functions, and this is exactly the same. Here, a function is reverse causal if the kth character of the output depends only on the kth character of the input and everything afterwards, and strictly reverse causal if the kth character of the output depends only on the characters of the input strictly past the kth character. And this doesn't have to be strict. In the run maps for the accumulator automaton, say with addition modulo 10, the kth character of the output depends on all of the characters before it in the input. Specifically, it's going to be the sum of all of those digits modulo 10. And so if we change one of those digits, it's going to change the resulting sum. On the other hand, I do want to be able to say that the character-wise functions are both causal and reverse causal. The kth character of the output depends only on the kth character of the input, but that's fine. We'll account that as the definition applying in this case. I was initially tempted to say that every causal reverse causal length preserving function has to be a character-wise map, but that's actually not true. You could have a function that completely ignores the input and outputs an alternating series of characters, a, b, a, b, a, b, up to the length of the input. In this case, the characters of the output don't depend on any of the characters of the input, and so it's causal and strictly causal and reverse causal and strictly reverse causal. Of course, not all regular functions have to be causal. For the function that turns all a's in the input that are next to b's into b's, the kth character of the output depends on the k minus first, kth, and k plus first character of the input. If any of these characters are b's, then the character in the output at position k is also going to be a b. And so in order to determine a particular character of the output, we need to look both to the left and to the right in the input, both to the past and the future. It's a little bit awkward to think about these functions, as usually when you see a word, you want to think of this as being read from left to right, character by character. But that's a little bit tricky because sometimes characters towards the end of a word can affect what happens towards the beginning. So unless you're okay with time travel, this isn't a particularly useful perspective. Let's take a moment to consider a causal, length-preserving regular function and the finite state automaton that recognizes that function. Now, you might be concerned that it's hard to, looking at just the language that the automaton recognizes, to be able to parse out the internal states of that automaton. After all, automata can have a bunch of unreachable states in whatever configuration they want to be in, and a bunch of unnecessary redundancy within the states that makes it really hard to reason about the structure of these things. Fortunately, though, we do have a tool for looking at a regular language and reasoning about its corresponding finite state automata, and that's the Myhill-Nerode theorem. It allows us to talk about the minimal finite state automaton that recognizes a particular language. And this minimal finite state automaton is not going to have any of these redundancies that a general finite state automaton recognizing this language might have. So let's say for a moment that f of ABBA is equal to CCDC. This means that our finite state automaton accepts the input AC, BC, BD, AC. And when we feed these four characters in as input to our automaton, we wind up in some sort of accepting state. I'll call it S. Let's say that our input alphabet only has the characters A and B, and our output alphabet only has the characters C and D. So there's only 4 possible characters that we could be feeding into this automaton. AC, AD, BC, and BD. And these are all going to be edges coming out of the state S. Let's say that our finite state automaton also accepts ABBA, CCDCD. That means that when we're in state S and we read an AD, we wind up in another accept state. And it could be the same state as S, but I'll draw it differently just for clarity's sake. But what about the edge AC? What would happen if we read in ABBA, CCD, Well, this certainly wouldn't be an accepted word because we know that f of ABBAA is CCD. But in fact, this is actually a doomed word. There's no way of continuing this input to get something that's accepted by this finite state automaton. Because this function is causal, the output character at this position can only depend on the input characters up to and including that position, which means it's not going to depend on other output characters, and it's not going to depend on further input characters. And so there's nothing that we can do later on to change this D into a C with an accepting pair. So that means that this AC edge must take us to a state where we can't, from that state, reach an accept state. It has to lead us to a failure state. And conveniently, by the Myhill-Nerode theorem, all failure states are the same, right? They are all states that have no futures. So they're all Myhill-Nerode equivalent to each other, so we might as well make it just one failure state. Similarly, one of BC or BD is going to be a valid continuation of the input, depending on whether f of ABB, BAB is CCDCD or CCDCC. Let's say that it's CCDCC. Then when we read in a BC in state S, right, the state that we got to after reading this much of the input, we're going to wind up in some state, and again, this could be the same as S or the same as T. We'll call this state U. And it's some sort of accept state because this input is accepted by our finite state automaton. And again, for the same reason, if we read a BD, right, this output character here is determined by these input characters here. So if we read a BD, there's nothing that can happen later on in the input to somehow make this accept, to be a correct input-output pair for our function. And so if we read a BD, again, we're going to wind up in a failure state. And by the Myhill-Nerode theorem, this can be the same failure state. And if we're in the failure state and we read any character, we just wind up in the failure state again. So we can actually say something really interesting about the structure of our automaton here. Within any state that's reachable in an accept state, we have, for each input character, one edge that leads to an accept state, possibly the same state, we don't know. And for all of the other output characters paired with that input character, it's going to lead us into a failure state. And we see the same thing with B here. We have one output character that leads us into an accept state, again, possibly the same state that we've seen before, and then all of the other output characters lead us into a failure state. And if there were other output characters like BE, that would also lead us into a failure state because there's no way of continuing AB, BAB, CC, D, C, E into a valid input-output pair for our function. Because again, our function is causal. This output character here is determined only by these input characters here. So we can actually say something really important about the structure of our automaton here. If we're in any state, this is a a generic situation, if we're in any state except the failure state, the input character determines the output character that continues us out of the failure state. So as long as we agree that we're not winding up in the failure state, the transition that we make is determined by the input character. If we're in this state and we see an A as an input character, then we go to this state, as long as we're not going to the failure state. If we're in this state and we see a B as an input character, then we go into this state, again, as long as we stay out of the failure state. And so we can construct a corresponding automaton that only reads in input characters, and the run, the sequence of states that we get for this automaton, is the same as the sequence of states we get for this automaton, provided we're staying out of the failure state. Again, as long as we're staying out of the failure state, the input characters determine the run of the automaton. Let's see this in action. So our finite state automaton, recognizing our causal length-preserving regular function, looks something like this. Here all of these are accept states, and then there's also a failure state that I haven't drawn, and all edges that aren't labeled go to the failure state. I've just omitted those things for clarity. And the key thing is that for any state that we could be in, the input character of the input determines where to go next. So if we're in state 2 and we read an A, then we necessarily have to read a C to stay out of the failure state. But if we read an A, we wind up in state 1. If we're in state 2 and we read a B, we have to read a D for the output, and we wind up in state 0. At this point, we can think of these output characters within the input of the automaton as less of an actual input to the automaton and more of just something that comes along that informs our output of the function at the end. Let's take a look at the run of this automaton on a particular input. This automaton starts out in state 0. And then suppose we read an AC, so we'll go to state 1, and then we read a BC, we go to state 2, we read a BD, go to state 0, read an AC, go to state 1, read an AD, we go to state 0. Now, each of these output characters depends in a pretty essential way on all of the input characters up to and including the one at that position. But if you remember our examples of regular functions, the really important one, the input to run map, was a strictly causal function. Can we somehow turn a causal function into a strictly causal function? Well, sort of. It's definitely the case that this D depends on this character here. If we changed this character to an A, right, if we're in state 2 and we read an A, we need to read a C, otherwise we'll wind up in the failure state. And so if this is an A, this has to be a C. So we can't determine this character just by looking at the previous characters. However, we can determine a function from inputs to outputs. A quick lookup table that says if you see a B, it's a D, if you see an A, it's a C. So let's create a function that, instead of directly outputting the sequence CCD, instead outputs functions, lookup tables, that tell us how to turn the input character into the output character. There are 4 such functions. Two of them are constant functions. I'll just call them the constant that they are. C is the constant function that always outputs C. D is the constant function that always outputs D. And then I'll call the function that takes in A to C and B to D, call that F. And then the function that takes A to D and B to C, I'll call that G. And so instead of having our function output a d here, I'm going to want it to output an f to indicate that if this character is a b, then this character here should be a d, and if this character here is an a, then this character here should be a c. I'm basing this on the fact that we're in state 2 going into reading this character. And so if we read a, b, a, this character has to be a c, and if we read an a, b, b, this character has to be a d. And generally speaking, if we're ever in state 2, we want this output character to be an f, because whatever character we read next, if it's an a, we're going to have to output a c, as f tells us to, and if we read a b, we're going to have to output a d, as f tells us to. So if we're in state 2, we want to output an f. If we're in state 1, on the other hand, if we read in a b, we should output a c, and if we read in an a, we should output a d. So if we're in state 1, we should output a g. Right? At this point of the input, if we read an AB, this character should be a C, and if we read an AA, this character should be a D. And then finally, if we're in state 0, if we read in an A, the output character has to be a C, and if we read in a B, the output character has to be a C. So we should output a C. And again, that makes sense. If this is an A, then this has to be a C, and if this is a B, then this has to be a C. So we can modify our automaton to look something like this. And now our input and run looks something like this. Notice that the run is the same because the sequence of states that we experience just depends on the input characters of the input and not the output characters of the input, and the output characters that we have at any one point depend exclusively on the state that we were in going into that input. And the state that we're in going into that input is determined by the input characters that we see before it. In other words, this f is determined by this a and this b. If I change this character to an a, right? If we're in state 2 and we read an A, the output character still has to be an F. So this character here doesn't depend on this character. We can change this character without this character changing. And yet we can still recover the original output of our function by applying character-wise these functions to these input characters. So if we call this original function here P, and this new function here, Q, we can recover the output of our original function by applying a character-wise application map. In our specific example, when I plug in ABBAA, we just need to calculate the character-wise application of these functions to these inputs, right? To take C of A, G of B, F of B, C of A, and G of A. And the result is going to give us the output of our original function, CCD. Keep in mind that I made no special assumptions about our original automaton. All I said was that this was some automaton that we got when looking at the Myhill-Nerode minimized automaton, recognizing a particular causal length-preserving regular function. And this P is our causal length-preserving regular function. And so what I've shown is that any causal length-preserving regular function, you have to generalize this proof, can be written as a composition of a character-wise application and a strictly causal length-preserving regular function. I like to call this sort of composition where we're not just feeding the output of the inner function to the outer function, we're also feeding the input to the inner function to the outer function. I like to call this a cascaded composition. So we have this fact: every regular length-preserving causal function can be written as a cascaded composition of a character-wise function and a strictly causal length-preserving regular function. Let's actually go a step further. Let's consider the run map for this, well, not this original automaton. I actually want this automaton here. I want this original automaton, but where the output characters are just completely missing. Again, the run that we have only depended on the input characters, so this isn't going to change the run. It's still going to be 0, 1, 2, 0, 1, 0. And again, because we want to be focusing on length-preserving functions, I want to take the truncated run map. Now, here's the thing. These output characters only depended on the state that we were in going into reading that particular input, right? If we were in state 0, we necessarily had to output a C. If we were in state 1, we necessarily had to output a G. And if we were in state 2, we necessarily had to output an F. So these characters here are determined by the states that we're in. In other words, if we define a new function that takes 0 to C, 1 to G, and 2 to F, then this output here, our Q of X, is just going to be H applied character-wise to this run here. Right? We apply H to the first character and we get a C, which is the first character of Q of ABBAA. We apply H to the second character, we get a G, we get the second character here, and so on and so forth. And there's nothing special about this particular input. We have in general that for any input word X, we can calculate Q of X just by computing the run map for M, the truncated run map on X, and then character-wise applying our lookup table. And so when we combine these two results, we have that our original causal length-preserving regular function could be written as a composition of character-wise functions and a truncated run map. And so if we want to study the causal length-preserving regular functions, all we need to do is understand the character-wise map, which we do, and then also understand truncated run maps. And we don't even have to worry about general run maps. If you think back to our discussion of monoids, all we need to understand are run maps for monoid accumulators on the monoid of functions from a finite set to itself. Let's see what this looks like in this example. We can think of each of these input characters as a function on the set of states. If we are in state 0 and we read an A, we wind up in state 1. If we're in state 1 and we read an A, we wind up in state 0. And if we're in state 2 and we read an A, we wind up in state 1. For B, it's this function here. So we can take this input string and we can turn these A's and B's into these functions using a character-wise lookup table. If we then apply our truncated run map for our monoid accumulator, well, this term here is going to be the product of all of the terms before it in the input. There's no terms here, so it's just the identity element, right? The identity element in this function space is just the identity function. The next term is going to be the product of just this term here. The next term is the product of these two elements here. Remember that the product in this monoid is function composition, so we compose these two functions. 0 gets mapped to 1, and then 1 gets mapped to 2. I realize that's a little bit backwards from function composition. Function composition is always annoying. It's always backwards. 1 gets mapped to 0, 0 gets mapped to 0. 2 gets mapped to 1, 1 gets mapped to 2. This next term is the composition of these three functions. In other words, the composition of this function, remember this was the composition of these two, and then we multiply by this, we compose with this, and we get 0 maps to 2, maps to 0, 1 goes to 0, goes to 0, and 2 goes to 2, goes to 0. This is now the constant 0 function, so it makes it much easier to compose. If we compose this with this, everything gets mapped to 0, and then that 0 gets mapped to 1, so everything gets mapped to 1. So if this was our x, and this here is our character-wise lookup, where this is our lookup applied to x, then this here is the result of our truncated, we don't care about this last character, run map for the monoid accumulator automaton applied to that. Now the result is actually a function that tells us at any point, let's take a look at this value here. This tells us if we start off in state 0 and we read an AB, we'll wind up in state 2. If we start off in state 1 and we read an AB, right, the characters before it, the characters that gave us these two functions here, if we start off in state 1 and we read an AB, we apply these functions to the states in that order, and we'll wind up in state 0. And then if we start off in state 2 and apply these two functions, we read these two characters, we'll wind up in state 2. But we know what state we started in. We started in state 0. And so if we take each of these functions and we apply them to 0, we get, right? Apply this to 0, we get 0. Apply this to 0, we get 1. Apply this to 0, we get 2. Apply this to 0, we get 0. Apply this to 0, we get 1. I'm going to call this function epsilon naught, the plug-in 0 function. And again, this result here is the truncated run map applied to this input for the original automaton. So as long as we don't mind composing with a bunch of character-wise functions to translate things in and out of various contexts, we don't even have to worry about general truncated run maps. We only have to worry about truncated run maps on this one very specific type of finite state automaton, the monoid accumulator for functions on a finite set under composition. And I realize that's a bunch of complicated notation, but when I talk about this truncated run map on this monoid accumulator automaton, all I'm talking about is a function that takes in a string of functions and outputs a string where each term is the composition of functions that appear before it on the input. Right? This was the composition of nothing, so the identity function. This output here was the composition of just this function here. This function here was the composition of these two functions. This function here was the composition of these three functions. And this function here was the composition of these four functions. So I want to end this video here, but we're still a long way off from understanding all of the regular functions. All I've shown is this one specific type of regular function, where it's length preserving and causal, can really be understood in terms of this very specific truncated run map that we saw here. But we'll need to go a few steps further. First of all, I'm going to want to really get to understand this particular truncated run map. And in a future video, I'll use the Krohn-Rhodes theorem to break these sorts of functions up into simpler functions that are easier to work with. On the other side, I'm going to want to loosen the restrictions that the functions that we're looking at be length preserving and causal. what happens if we look at non-length preserving regular functions? What happens if we look at non-causal regular functions? It will turn out that we'll be able to understand those more general types of functions in terms of these very specific functions that are length preserving and are causal. And so ultimately we'll be able to describe general regular functions in terms of whatever we wind up using the Krohn-Rhodes theorem to break these functions down into. So thanks for watching, and leave any comments or questions that you have down below, and I hope to see you in the next video.